Okay, so good morning, good afternoon, and good evening, depending on where you are, to all of the participants in our virtual journals club. Today, we are hosting the journals club on the PRX paper called The Robust Encoding of a Qubit in a Molecule that has been published a while ago by Victor Albert, Jacob Covey, and John Preskill. My colleague Mauro Schulaz from PRX and me, my name is Stojan Rebic and I'm working from PRX Quantum. We will be hosting this meeting, which will be moderated by Dr. Arne Grimsmo from the University of Sydney. Now, before we go to the talk itself, let me tell you a few words about how is actually this meeting organized. So, as you know, we are all in Zoom, and inside of your Zoom app, you will see the presentation for the Journal Club. After the presentation, which will last for about 15 to 20 minutes, is over, you are free to ask questions. Now, you can ask questions either by typing them in the chat, which you can see down here, or you can raise a hand in the participants window. Arne, who's a moderator, will then pick up and ask you to unmute and to show yourself on a video to ask the question. We would very much like to foster the person-to-person communication. So if you can in any way show yourself on the screen and turn on your video and ask your question in your own voice, we would very much prefer that. So, with that in mind, before we start, I would like to also say a few words about our newest journal in the family. It is called PRX Quantum. It has started to accept submissions earlier in the summer this year, and it has started publishing its content in September. So there is quite a number of articles already there. The point of PRX Quantum is that it is a high-level, high-profile journal that is oriented to the quantum information science and technology community. And unlike previous physical review journals, we would like to also spread into the adjacent areas of computer science, mathematical aspects of quantum information on one side, but also an engineering aspects on the other side, implementation, particular implementation, so that the journal will serve as a home to the entire community. With that in mind, we are also publishing a novel content, so the novel types of articles there. And I'm pleased to tell you that the first of these novel articles have been published just about 10 days ago. It is a perspective article on harnessing the power of the second quantum revolution, written by Ivan Deutsch. Perspectives are supposed to be forward-looking articles that are intended to show the broad quantum information community what are the outsetting problem in the field, what are the perspective areas in the field, and what is useful to look at and explore in the future. This inaugural perspective is very broad in its nature, but those that will follow will be much more focused on a particular subject. We want to communicate to the entire quantum information science community, so the perspective should be written in such a way that they, although they are focused on the one particular area, they would appeal to the other area, so the people across the community can actually connect and learn about what is being done elsewhere. And with that in mind, I would like to stop sharing my screen and turn on to the moderator, Dr. Arne Grimsmo from the University of Sydney. Arne, it's yours.
Thank you for that, Stojan. Okay, so it's my pleasure to introduce Victor Albert, the speaker. So Victor is a physicist at the National Institute of Standards and Technology and an assistant professor in the Department of Physics and the Institute for Advanced Computer Science at the University of Maryland. Victor works in the broad array of quantum science, technology, engineering, and mathematics, with topics ranging from superconducting circuits to molecular physics. He's made important contributions to open quantum systems and bosonic codes, amongst other things. Victor received his PhD from Yale in 2017, and he was a postdoc at Caltech before starting his current position. So over to you, Victor.
Hi, everyone. It's exciting to be able to have such a great audience to present things. And I guess silver lining of coronavirus is that it forces us to communicate in more efficient ways. So let's hope that this was fruitful. I'll be giving a brief, fairly qualitative overview of the results and motivation in these few slides. So as Arne mentioned, I was a postdoc at Caltech, where basically this work was done. Now I'm at NIST, but stationed in Quicks at the University of Maryland. And the sort of motivation and my background coming into Caltech when I started working on these ideas was in part in continuous variable systems. And such systems are characterized by continuous degrees of freedom, such as the position and momentum of a mechanical oscillator or quadrature components of an electromagnetic field mode. They're prominent in many important physical settings. There's 4 that I can list here. One that motivated me greatly in grad school and continues to do so is the setting of 3D or 2D microwave cavities implanted with superconducting circuits. Continuous variable degrees of freedom also describe the motion of mechanical motion of trapped ions or physical motion. They are also prominent in nanoacoustic or mechanical resonators that are currently being made with lifetimes that are exceeding even those of the microwave cavities. And of course, they're used to model the space of an optical fiber. As the signal travels through the fiber, it attenuates in a way that's similar to a microwave pulse in a cavity slowly losing photons within the cavity by leaking out. So I've listed some people below. There's of course many, many others. These are just the people whose pictures I took. These systems, of course, all suffer from noise, and error correction is necessary to scale them up, both in terms of the size, in case you're wanting to do a quantum computer, large quantum computer, and length, in case you're interested in building a quantum network consisting of many links and connected by different wires. So these applications, the latter is usually prominent in the optical setting, and the first 3 are active efforts in terms of scaling up computing devices. So how do we error correct in such systems? Well, 20 years ago, Gottesman, Kitaev, and Preskill developed error correcting codes that could protect against simultaneous shifts in both the degrees of freedom, the conjugate variables that I mentioned, position and momentum. So to the right, here I have this oscillator phase space that I sketched out. And I just wanted to briefly sort of give you a taste of these codes. The way they work is as follows. So a code is a subspace of your system Hilbert space or oscillator phase space. And as a proper subspace, they can be introduced by defining a set of states called a basis states for the subspace that you would prefer to be orthonormal. And one way to do this for the GKP codes is to use coherent states. So these are just normal coherent states of the oscillator, alpha, superimposed in the respective lattices denoted by the black and white balls for the 2 respective code basis states or code states. And to give you a flavor of why this particular definition of a subspace protects against small shifts, you'd like to see what happens when these 2 code states are shifted by a small shift. So such a shift can be an arbitrary direction in the phase space, so it can be generated by an arbitrary superposition of position and momentum, P and X, or X and P. And you can see from the diagram, I hope, that as long as this shift is small enough, each circle, each ball in the respective lattices stays within its own unit cell. And so it is simple to infer where it came from once you just snap it back to the center of the unit cell that it's in. If the shift in the lattice is sufficiently large so that it takes the each ball outside of its unit cell, then this recovery that snaps each ball to the center of the unit cell that it's located in fails, because the black balls will go to the white balls and vice versa, and that'll yield a bit flip error. But nevertheless, if the shift is small enough, once again, you can roughly see that all sufficiently small errors can be corrected. Now, this is done by measuring a set of operators that basically measure the position and momentum of the oscillator modulo the spacing between the unit cells. So you cannot measure position and momentum simultaneously, but you can measure position and momentum modulo some numbers. These were thought to be not very realizable. Maybe John can comment on the history here. But 20 years ago, as in the past few years, they've been realized in two different platforms, in trapped ions and in superconducting circuits, which is fairly exciting for these codes, because they've also gained the attention of industry in terms of providing a viable blueprint for a scalable quantum computer. So I was pretty involved with these codes starting my postdoc, and I thought that maybe it's possible to transplant some of this intuition behind them and their robustness to other continuous variable systems. And one continuous variable system that I found was quite interesting was a rigid body. And the orientation and angular momentum of a rigid body can also be thought as a pair of more advanced conjugate variables. Now, rigid bodies come in many shapes and sizes. They include airplanes, robot arms, and molecules. So we'll consider the third for the near-term quantum applications for the purposes of this talk. And that's because significant progress in controlling these molecules and stabilizing quantum states and superpositions of different states in these molecules has been made. The goals here, the applications in mind, are quantum computation as well as precision measurement. The particular molecules that people have been succeeding in trapping are usually small, of course, consisting of two atoms, as well as 3 or more atoms. And there's a handful of groups working in trapping these molecules such that their center of mass is pinned, and such that you have access to their rotational degrees of freedom as well as their nuclear degrees of freedom, while cooling as much as possible the electronic and translational degrees of freedom. So you'll see in the next slide that such spaces, the rotational spaces of these rigid bodies, are substantially more complex. So it's not clear at first why or how error correction can be even done for such systems, and that was the question that we undertook in this work. So to introduce the configuration space of these molecules, of these rigid bodies, I'll first mention, the stuff that everybody knows, that the configuration space or position space of a harmonic oscillator is parametrized by the real number line, which can be associated with the group of the reals under addition. And in 2 dimensions, but a 1-dimensional rigid body, its different orientations are characterized by the real number line, but periodically identified, namely a circle, which can be associated with the group U1. And now comes the step sort of in the new direction. And that deals with how to characterize the configuration space of a 3D rigid body, which is now allowed to orient itself in any direction in three-dimensional space. Well, let's take a look. If we set the rigid body in a certain fixed initial orientation, then we can apply a rotation, a 3D rotation to it, taking it to a different orientation. As such, the rotation is characterized by an axis around which you rotate and by an angle by which you rotate. I'll denote the axis by V and the angle by omega. So we've applied this particular rotation. Now, if we start with the same initial orientation and apply a different rotation, we will get another orientation that's distinct from the previous result. And the reason we get a different orientation is because our molecule, our rigid body, is asymmetric. And namely, any rotation applied to an initial configuration will give us a different configuration, which means that we need all possible 3D proper rotations to characterize the configuration space of this rigid body. And this means that the configuration space of quote unquote position states of our rigid body is characterized by rotation matrices in three-dimensional space. Now I can take the angle and the axis and multiply them together to depict this space in this ball configuration. But all I want you to take away from this is that GKP codes have been done for these abelian configuration spaces, namely configuration spaces associated with these continuous but abelian groups. But it's unclear because of the extra level of complication whether it's possible to do this for this non-abelian group characterized configuration space. Right. And so this is what we, this is the question that we answered. We developed a framework of, an error correction framework of molecular codes for 3D rigid bodies. And I want to remind you that these rigid bodies have conjugate degrees of freedom that characterize their orientation, position, and their angular momentum. And our codes can protect for small rotations of the body, so namely small displacements in the position degree of freedom. And these displacements are more complicated because now they include rotations about any axis, as well as small displacements or kicks in the momentum degree of freedom, small kicks in the body's angular momentum. So once again, the logic behind GKP codes survives. As long as both of these shifts are small enough, we're able to correct, but once they become significantly large, it won't be possible. Just a little bit of math here. The codes are based on discrete subgroups of picking discrete subgroups of the configuration space. So for the GKP code lattice that I depict here, the lattice can be thought of as, R squared, and the subgroups are basically the integers. For SO3, for this SO3 ball that I drew, you can pick subgroups that are characterized by discrete rotations by multiples of 2 pi over n, which are just the subgroups Zn. But what's interesting and unique about this space is that the subgroups themselves can be non-abelian because the configuration space is non-abelian. And so here we've also developed or investigated codes based on non-abelian subgroups that give you slightly different error correcting properties. We can extend our codes, or we've also examined codes, similar codes, that can be used to protect information in the rotational degrees of freedom of a diatomic molecule. So a diatomic molecule in the middle here, it is symmetric under certain rotations, namely rotations about its primary axis. And so those rotations have to be divided out because they're not necessary to describe the configuration space of this molecule. This is actually not good for error correction because good error correction requires redundancy, and modding out or dividing out degrees of freedom that we were otherwise able to use in the asymmetric case actually reduces the size of our available space to use for error correction. and actually winds up hindering some of the error correcting properties that we enjoyed in the asymmetric case when we reduce it to the symmetric molecule case. I can discuss that in the discussion later if you'd like. But I'd also want to mention that our codes can also be used for sufficiently large nuclear state manifolds of both molecules and atoms using spin coherent states to approximate the code states. So GKP codes were realized, as I mentioned, 20 years later. We've extended them to these more exotic phase spaces. We believe this is an ambitious but not ridiculously ambitious path for the community to try to develop aspects of these proposals. I just have one more slide. We had sketched out some ideas for trying to realize aspects of these proposals. And I'll just mention a few of them here. So we have 2 conjugate degrees of freedom, the orientation of the molecule and how much momentum it has. So we'll need to correct against both. So to correct against the first, we need to perform rotations that are conditional on the outcome of the measurement that we have to do in order to find out how the molecule has oriented itself under the noise. And this requires entangling with some ancillary system. And we were thinking that maybe we could use the nuclear system as this ancilla. And there is a natural nuclear spin coupling that between the rotational and nuclear degrees of freedom. As far as I understand, it's not particularly strong, but it is an avenue that I think is worth exploring. To correct against momentum shifts, we need to shift discretely the angular momentum of this molecule. And this is, I think, a more wide open question. People have studied this in the context of these rigid bodies confined to the plane. But I think this is something that should, we hope will be investigated for the 3D, the more complex 3D option. And can go over what the stabilizer operators are, the ones that measure position and momentum modulo something for these molecular cases. But here I just wanted to point out a paper that had written down one of these complicated stabilizers that we had been developing back in 1936. And the reason they did this is because that stabilizer is precisely describing the potential that a lattice imposes on a molecule that's trapped inside the lattice. The lattice has, say, a tetrahedral or some other symmetry, and therefore the potential imposed on a defect in the lattice will have that same symmetry. And that is precisely the same type of, trait that our stabilizer Hamiltonian operator shares. So that was quite interesting to me. But I guess last and probably not the least by far, in terms of near-term realizations, is how to make the states. And such a scheme requires many microwave pulses to address the individual energy level differences of the rigid rotor, rigid body Hamiltonian, symmetric top, whatever you want to call it. But it's not unrealistic to consider such sort of brick by brick schemes that build the specific states of our encoding level by level. And the primary reason for that is because we have an inherent anharmonicity and therefore a higher addressability of these molecular systems. So in the corner here, I've put sort of an approximate version of our code state that we hope will be realizable soon. And so that's it for my talk, and I thank you for your attention.
Thank you very much.
I'll leave it.
Victor. I guess everyone can put the reaction they want up to clap. Yeah, so please start typing your questions in the chat. I might just give everyone a few seconds to type, and then I can start off with a question myself, maybe while people are typing. So I guess one of the things we heard last week in the Q&A session was that when the GKP paper came out, people thought it was beyond impossible. Have you talked with any experimentalists about the feasibility of creating these states, Victor?
We did even better than that. We have an experimentalist co-author. Every experimentalist, yeah, Jake has been helping us basically develop schemes that aren't all completely far out, like the first 3 points in the slide I'm sharing. Jake helped us with the 4th point with this particular microwave dressing scheme, which requires a lot more work than what we've written in the appendix, but it's not something that's completely out of reach. And other people like Alexei Gorshkov have studied similar type schemes. So experimentalists like Diederik Liebfried and Jun Yi believe that these types of schemes this particular microwave dressing scheme can be done. It's the first thing that pops into everybody's head. So I wanted to focus maybe people's attention on that as the most near-term application. In terms of, besides making the states, performing actual error correction, getting the stabilizer Hamiltonian to be created in the lab, those are goals that are significantly farther down the road, I think. But you never know, because Yale, in their superconducting circuit realization of GKP codes, they not only made the states, but they also did the active error correction in a continuous fashion, utilizing way fewer resources to measure the syndrome than we would have ever thought, than I would have ever thought. Instead of measuring position and momentum, they just measure the sign. So maybe some of those schemes, it would be great if they could be adapted to the molecular setting.
Right. Okay, there's a bunch of questions in the chat. I'll just move on to one of the audience questions. So first question is from Jonathan Holm. Jonathan, can you unmute yourself and ask the question?
So hi, I guess I was wondering, you referred to nuclear spin in atoms as being a possibility, but what about high L Rydberg states? I mean, you've got a lot of states available up there, and one would think that there's a pretty well-defined angular momentum. So is that a possibility for realizing the sort of schemes you're talking about?
Yeah, I think we try to mention that a little bit. One thing I'm worried about before I say what the system is lifetime of these high energy states. But if you fix the total angular momentum and just consider the different levels characterizing its z-axis projection, then you have effectively a finite approximation to the space of a 2D rotor that's confined to a plane. So the sort of U1 type GKP codes can be realized in that space, at least approximately. Now, from what I learned from discussions with Charles Clark and others, is that the entire Rydberg system can be thought of as an SO3 space via a basis change. This is known from 30, 40 years ago. But basically, I'll simplify it. If you take the hydrogen atom and you look at all its energy levels, they're characterized by N, which is present in the actual energy, and then the angular momentum L, and then its projection M. So these NLM states can be rotated into the angular momentum states of a rigid body by, I believe, writing the hydrogen atom in parabolic coordinates. So there's at least this abstract connection there to our codes. But again, experimentally, I'm not so sure that hydrogen atoms are stable enough to really give these to generate these long-lived states.
Thanks.
Okay. Next question is from Arian Jadbabai. Do you want to unmute yourself and ask Arian.
Yeah. Hi, Victor. Thanks for the talk. You mentioned, related to this question of truncating the spin space, just wondering, like, how does that affect the code? Like, how big does it have to be in order to kind of be able to be an effective approximation?
So we've tried to answer that question for truncated versions of the rigid rotor molecular spaces. We haven't looked into, oh, I should change this, this is old. We haven't looked into how to truncate it or how big a nuclear space needs to be. So unfortunately, I can't answer that question. But I do want to mention that, you know, so we have these truncated in angular momentum space versions of our states, and we did some fairly involved calculations trying to figure out, you know, how good the error correction can be if we truncate the states. The error correction for these types of codes, for both GKP and molecular codes, unfortunately, is best when the states are not truncated, which means when they have infinite energies and are precisely pinned superpositions of different orientations. Since those states are unphysical, we have to sort of smear the precisely pinned orientations over, say, some distance determined by some Gaussian around that position. And once we do that, we'll get an intrinsic error because the Gaussians have tails and they'll leak into places where we don't want them to be. And so the calculations we did involved calculating what average angular momentum is required for the truncated states to basically have less than 1% such intrinsic leakage error. And we got the answer to be about 8, I think, for 1%. But maybe I could be not quoting that correctly. But somewhere between 8 and 15 gives you pretty good intrinsic error. And to compare that with experiment in terms of addressability of these higher lying momentum states, Diedrich Liebfried's and David Lebrant's recent papers have been able to access about angular momentum at about 6 or less for a diatomic molecule. So it's comparable. It's not there yet, but it's definitely comparable.
Did I answer your question, Arian?
Yeah, that was great. Thanks, Victor.
So next question is from Aljosa.
On the possibility of using vibrational states of molecules for implementing these molecular codes.
I heard something about possibility of using vibrational states. I think there's been a long-standing effort by I'm forgetting the names, but people in the quantum control / quantum chemistry community thinking about vibrational states. We cite them in the paper. Yeah, realizing GKP codes. So GKP codes have, you know, are defined on this phase space of an oscillator, and vibrational states are in the same phase space. So realizing GKP codes with vibrational states would be super cool. I don't know the details of those, of how quickly that can be done.
Thank you.
All right, next question is from Will Cairncross.
Hi, yeah, I think my question was already pretty much effectively answered. Thanks, though.
Okay, all right. And then we have one from Moritz Schmidt.
Yeah, hello. One question. So the idea of these error correction codes is usually to like delocalize the information, right? But now you have it all in one molecule. Like, is there some correlation between the like dephasing and loss of coherence that could hinder this kind of realization? Or?
So the molecule's phase space is quite big. all these different orientations, you know, in principle, at least on paper, are orthogonal. They're orthogonal in the Dirac delta sense, so they don't exist in the real world, but still. So, and all error correction requires is a big Hilbert space. It doesn't matter whether that Hilbert space is spatially not occupying a lot of space or not. So I think it's, you know, I think these types of codes in terms of robustness are fairly comparable to the GKP codes and to non-topological CSS codes. So from the discrete qubit, discrete variable land. Now, what was the second part of your question about decoherence?
That was it. Yeah, I mean, it was if decoherence could be correlated, but then
I think when you say the word correlation and decoherence, it reminds me that, you know, for a scalable platform in this context would require many molecules, each one housing a qubit, each one pinned, and all of them entangled if you want to do an algorithm. And that's where things, you know, quickly start to decohere and become fairly macroscopic. So this is something of an open question about how to, even though the molecules are very compact, which is a big plus over, say, these 3D cavities, it's requires a very high level of control to be able to entangle many of them.
Okay, thanks.
Maybe I have a follow-up question on that, Victor. So if you want to do 2 qubit gates and such, or 2 molecule gates architecture, you just sort of have to move them close together, or how do you get that interaction?
Well, you still see the slide, right?
Yeah.
The molecules, yeah. So what people usually do is they, you know, use the naturally occurring interactions between the molecules, dipole-dipole interactions, to perform, you know, some sort of transfer of information or gates. But if you want to perform a gate between 2 encoded molecules, a dipole-dipole interaction will not be enough. You need higher multipole potentials to perform logical gates. I like to think of the analogy pointed out to me by Ben Agenbaum and John Doyle's group, that it's the same reason you can't perform a logical gate on the toric code by doing a single physical qubit rotation. The point of the codes is to store information non-locally. So if you want to store it non-locally, you're going to have to manipulate it non-locally. And the notion of locality here is, you know, small multipole, small dipole, and maybe quadrupole is local, but octopole, etc., is less. So, you know, this is a necessary evil in order to robustly encode information in these systems in this way.
Okay, thanks. We have a question from, let me just make sure I don't skip anyone. I think the next question is from David Patterson. You there, David?
Can you hear me?
Yeah.
I understand this brick by brick of building these exotic states. That actually sounds more or less straightforward once you can do one brick. But I guess my
Oops. I think he cut out.
that could that I don't know.
Did you hear that, Victor? Because you cut out for me.
No, maybe you could try turning off your video for a sec while you ask the question.
I can do that. Yes. My question is, could you give maybe a cartoon sketch of what this experimental realization of a higher multipole potential would be? It sounds like the brick by brick part I can do with microwave fields, with dipole fields, if you like. But this next thing, I mean, I don't know, I can't even visualize how I could apply an octopole potential to a molecule given, you know, Maxwell's equations. So maybe there could be some, just what that would look like.
Unfortunately, I can only give you the matrix you're going to need to do. I think I have the same type of, as little an idea about how to actually realize this as anybody else does. So I do want to give you the matrix though. So there's two types of stabilizers. There's sort of I want to say an analog of Pauli Z, an analog of Pauli X. Pauli Z is diagonal in the computational basis, in which in this case is the rotational basis. So the rotational basis is characterized by, in this case, Euler angles. Okay, so your electric field on the z-axis, I think, will be just cosine beta, a matrix of cosine beta diagonal in these alpha, beta, gamma states. Unfortunately, as I was saying, that's not enough. So you need, these powers of different cosines of beta in addition to cosines of alpha and gamma in this way. So why do you need that? Well, because this is the smallest potential that'll stabilize, that's minimized at 2n different points, which correspond to rotations around the z-axis by multiples of 2 pi over 2n. So this potential has, let's say n is 3, it has 6 wells in this configuration space of the molecule, and the 6 wells are the 6 rotations by 2 pi over 6 multiples. Now, our code states are superpositions of these different orientations. So the even ones are superimposed in the black balls in the picture. The even ones are superimposed to get the logical 0 state, and the white ones are superimposed to get logical 1. And to get the superpositions to be stabilized, we need to add another operator to the Hamiltonian, which is this X-type stabilizer that is just shifting you, rotating you by 2 pi over n, not 2 pi over 2n. So they skip a ball. And this type of, operator projected in the 6-dimensional space stabilized by the first one is just a direct sum of 2 Qubit Pauli operators. And, if you remember Qubit Pauli operators, their +1 eigenstate is an equal superposition of the canonical basis elements. So I'm sorry for not answering your question, but instead giving you a crazy looking matrix. But unfortunately, that's all I have. Maybe John can comment.
Well, I'm afraid it's just math. It's up to you, Dave, to figure out how to do it in the lab.
You guys are bastards. Thank you.
All right. Then we have a question from Siva Prasad, Omanar Kutan.
Hi. So my question is so when you told about detecting these errors using nuclear spin, so what happens if there is no coupling between the nuclear spin and the angular momentum, like for instance in the case of the ground space of the strontium atom? So can we still do this error correction in that case?
Well, then you'd have to look for ways to couple to another system, or try to engineer some coupling between the two through another system. Basically, in general, any error correction requires some sort of ancilla to monitor the system in some fairly clever way to extract just the right amount of information to diagnose the error, but not any more information so that you actually screw up the actual information being stored in the main system. So short answer is you'd have to look for another ancilla to use, or you'd have to look for another way to couple to the nuclear space if you still want to stick to the nuclear space.
Okay, thanks.
If there are further questions and you don't want to write them, you can also just raise your hand and I'll call out your name. Or just write in the chat that you have a question. Otherwise, I can maybe ask just a bit sort of on the history of the project, like what made you think about encoding quantum information in rigid bodies in the first place, Victor? Like what led you down this path?
Well, it was a pretty long path. When I entered my postdoc, John finally was able to explain to me something that I knew existed, but I didn't understand, which is this Fourier transform for non-abelian groups. And maybe I think it's kind of important, so I hope I can find the right slide on this thing. Yeah. So, I mean, here it is for the SO3 case, but for general groups, it's pretty much the same. Basically, we were able to sort of sketch out GKP code extensions for general groups early on, and it took me about a year to actually think of an actual application. That was done by talking to and looking around, even Caltech, and seeing people work with molecules, remembering some physical chemistry books that had these spaces basically hidden in them, expressed at least in terms of the momentum state, so the second equation. I guess the key trick was realizing that there's this Fourier transform that connects between the basis that we love to introduce error correcting codes with, the first line, and the basis that molecular physicists love because it's the one that accurately describes the real world, which is the second line. And once we sort of, things clicked into place when we realized that this SO3 group is actually relevant to molecular physics, and then we had to work out all the details, and that took another year.
Yeah, I think Victor would probably say this too. I have always loved the quantum theory of the rigid body, that the power of group representation theory is so impressive in that setting. And I always like trying to connect different ideas together because that's fun, and sometimes it can seed progress. So the challenge of, I also like GKP codes. So the challenge of understanding how GKP codes would work in the context of the configuration state of a rigid body was very appealing. Now, I don't think either of us would have appreciated that this was not just the ranting of two wild-eyed theorists, if not for Jake, who actually, we thought, he'd throw us out of his office or something, and he didn't. Or maybe he's crazy too, but I don't think so. On the other hand, we were in my office, so maybe that explains why he didn't throw us out at the time. Actually, Arnie, you brought up the issue of, 20 years ago, GKP codes seeming very unrealistic to experimentalists. That's partially true, but it's not uniformly true. Actually, part of the inspiration for proposing GKP codes came from the optimism of Jeff Kimball at the time that he could, using cavity QED, create designer states of the electromagnetic field using atoms in a cavity. And so, he speculated that he'd be able to build a little machine where you could specify any state in a superposition of Fock states up to some maximum photon number, and push a button and make that state. So it was natural to wonder what that capability would lead to. And Jeff was not completely dismissive at the time. I thought at that time, cavity QAD had the best possibility for realizing this. Circuit QED hadn't yet been invented, and maybe it was a glint in Rob Shelkoff's eye at the time. Actually, just as an anecdote, I first heard about circuit QED when Rob gave a talk at the Gordon Conference. I think it was in 2003, and Jeff was also there. And Rob talked about how, this was a natural arena in which one could do the things that in cavity QED and more powerfully. And Jeff said to me afterwards, boy, if I were a graduate student, I'd work for Rob Shelkoff. I don't know if he gave that advice to his own students, probably not, but it was good advice. And I guess another early enthusiast was Akira Furusawa, who is now at Tokyo leading a photonics group. He had been a postdoc at Caltech, and not that long after the GKP paper, I don't remember the precise date, but he came back to visit Jeff's group. You know, he had been a postdoc in the Kimball group, and he ran into me, and it was almost like it was a setup. He said, "Your paper is my Bible." And he was wearing a sport coat at the time, and he pulled out of the inside pocket the paper. It was all folded up, and he said he always carried it with him. I wasn't sure if that was a joke or not. But anyway, he is still, you know, eagerly in pursuit of GKP codes. And, you know, I think it's kind of cool that if you look at the, I'm not sure what he stuck around, but if I looked at the list of attendees here, you know, that we have molecule enthusiasts like Dave Patterson and Wes Campbell and Eric Hudson and the Doyle group, but also Jonathan Holm is here, and Luigi from the Yale group. And you know, I just think that kind of connection between people working on different platforms can lead to exciting progress. So, you know, if we help to facilitate that, I think that's a good thing.
Yeah, that's really cool. Any further questions? I think you can just unmute yourself at this point if you want to ask anything.
Hi, I have a question.
Yeah, go ahead.
The Wigner rotation matrices are usually thought of, as shown in the equation over here, is rotating, you know, a system, a quantum system into any direction. But it's also an eigenstate of a charged particle in a magnetic monopole field, the angular momentum states of magnetic monopole. Is that of any interest, or could that connection be useful in any way?
Yes, I found that exciting as well. So the hydrogen atom, rigid bodies, and what you said, particle in a monopole. I think at one point I remember that they were all related by a basis transformation, the Hilbert spaces. I can't answer your question though, because I don't know any robust experimental platforms for what you mentioned.
Okay, maybe I'll ask another one then, Victor. Do you think, like, other than molecules, do you think this could maybe be simulated in some way in some other system? Is there, you know, a circuit QED realization that could perhaps simulate the setup?
Yeah, so I mean, basically my answers about these questions about simulations are basically excerpts from our section 3, where we write about experimental realizations in a language that we were hoping was accessible. So one thing that came to mind after your question is, so you take 3 oscillators, you know, X, Y, and Z, and you cook up a potential that pins them to the surface of some, to some sphere, to some constant radius, X squared plus Y squared plus Z squared equals a constant. And that's a 2-sphere, which is the configuration space of a diatomic, heteronuclear diatomic, namely a rotor confined to spin in the plane. You take 4 oscillators, XYZW, pin them to a 3-sphere. That 3-sphere is the same as SU2 because of this quaternion connection between the, between the Pauli matrices and quaternions. And so SU2 is basically a factor of 2 away from SO3, which is the Hilbert space of configurations of a rigid body. So 3 oscillators, you get a diatomic. 4 oscillators, you're more or less up there with the full polyatomic rigid body. That's one idea we thought of, but again, it's like many of the ideas, unfortunately, in the paper, it's only on the level of the Hilbert space.
I see. So the actual interactions are very complicated in that simulation, or actual gates you need?
I think the notion of locality still carries through, namely that, distances on this sphere are, follow the same notion as distances sort of in the space of orientation. So if you shift this orientation a little bit, that's smaller of a shift than shifting it a lot, namely, and that's the same as when you have 3 oscillators confined to a sphere. So it's a physical simulation of the space. In terms of how complicated the gates are, they would involve, entangling gates of all 3 oscillators, because you need to write things in terms of these polar coordinates of this, this particular sphere. So there would be fairly complicated operations you have to do. You have to have good control of all 3 of these things and couple them really well.
Yeah, I see. All right, thanks. So I think we're pretty much, I think Stojan wants to say a couple of words before we end. So I'll just hand over to you, Stojan.
Sure, thank you. Well, first of all, I would like to thank all of the participants of this journal club. And of course, first and foremost, Victor and John for presenting their very interesting work here. Thank you to Arne for very skillfully moderating this session as well. So before we go, I would just like to mention that the recording of this session will be available in a few days' time on the Journal Club website. Before we go, however, I would like to announce next Journal Club that will happen next Monday, 11 a.m. Eastern Standard Time. So with that, I would like to say thank you to everyone, and I will see you. We will hopefully see you next time. The website for the Journal Club is in the chat box if you want to go there and check it. Thank you.
Thank you. Bye-bye.
Bye.